Hello everyone. Am I audible to you all? Right. Good. Uh, I think all of you have revised the yesterday's two classes, right? Okay. And uh, today's boot camp would be more interesting, right? Uh, and let's just wait for 2-3 minutes. Uh, then we'll start. Okay. Nice. Okay. If any doubt related to the last 2 days, you can just ask me. Okay. Okay, nice. Okay, so before starting, I tell you that how our today's structure of the bootcamp would look like. Okay, for today is the day 3. So today you'll learn about the threads again, though they are covered in the previous lectures also. Right, the race condition, critical section, and mutex and semaphores. Okay, not the basics, but everything about them. Okay, that why they are used. Okay, in interviews, they directly ask that why mutex and semaphores are used. Okay, so very basic questions are asked from these topics. Okay, though there are higher level things, I don't think so that is required at all. Okay, okay, like I'll tell you. Okay, I think we can start now. Okay. So before diving into that, what is race condition, critical section, and mutex and semaphore? Okay, uh, okay. So what we'll do, we'll just revise that. What are threads? How multi-threading is better than the multitasking? Okay, and then we'll continue with all these. Okay, so this much all of you must have covered. Okay, these you will cover today: flags, mutex, semaphores. Okay, so we'll be covering we'll be covering the what is about the threads. Okay, so I already told you that suppose this is a process p1. Okay, this is a process p1. Okay, so threads are actually the lightweight processes of P1. Like P1 is dividing itself into multiple processes like P2, P3, etc. So you can just think of these dots as threads. Okay, and the reason that why multi-threading means the running of multi-thread simultaneously is better than the multitasking. The reason is that the okay, let me just draw, then it would be more clear to you. Okay. So what happens in multi-threading? You are switching in the one address itself. Okay. So when you are switching within one address itself, the switching is happening at a very fast rate. Whereas what happens if you are doing multitasking, you have to change the address from P1 to P2. Okay, so what happens, what you are doing, you are changing the whole address itself. Okay, due to which it is not very much fast process. Okay, so I think this particular point is clear, that what is multi-threading and multi tasking. Okay, and there is another term which you should know, though the term you would be very much familiar with, is concurrency. Okay, these all terms are very much what you say are covered in your what you say notes. Okay, so this is the day 3 notes that we'll revise at the end of the class, but I'm just telling you the what's the like the definition in a very simple manner, so that it gets to your brain very in a very simple manner. Okay, so talking about concurrency, so concurrency is nothing, it refers to the execution of multiple instruction in parallel manner. Okay, so like what is happening, talking about the threads. So the concurrency is achieved when these threads work simultaneously, so that our the output that we need, we can achieve it in a more fast way. Okay, so this is what actually concurrency means. We can just look the definition from here. This is the critical section, I think. Okay, it would be covered in the last. Okay, so just to keep in your mind that what is concurrency, you can also, like, you would be very much familiar with this term. Concurrency means concurrent things are happening in a concurrent manner. Okay, so we want to achieve concurrency so that our processes can be done at the faster pace. Okay, so I think the this was just the brush up of the previous classes. Okay, if any doubt in this, you can just ask me. Okay, like in multi-threading, what is concurrency? Okay, you want that, let me just make it clear. Suppose this is P1. Okay, this is P2. Okay, you want that if P1 is independent of P2 and vice versa, so you want that they should be, what you say, they should be executed in the same time, because they are not interfering in each of the process. So what you do, you want that they should be executed in the same time. So this phenomena of execution of two processes which are independent is called concurrency. Okay, and concurrency is achieved in the multi-threading, because we know that when you make threads of a particular process, those threads are independent of each other. Okay, so let me just see if any doubt. So can you tell threads in a simple term? Okay, okay. Let me just say, if you open the Word file, I think, let me just think a good example. But for the simple definition, what is this? That P1 is a process. Okay, P1 is a process, right? And its sub processes, which are lightweight processes, are the T1, T1, T2, uh, T2, and T3. Okay, we divide the process into these threads in such a way that they are independent of each other. Okay, so as they are independent of each other, what will happen? We'll achieve concurrency in a very fast manner. So suppose what you are doing, that uh, suppose you open the Word file. Okay, and you start editing the text. While editing the text, you change the color, and you change the font size at the same time. So what happened, that changing the font size and the changing the color of the text are both separate process, but you see that they happen in what you say, at the same time. So this is what happened. You open the Word file. So opening the Word file is a process one. Okay, you are editing those Word file, let's say T1 and T2. T1 refers to the changing color and T2 refers to changing the font size. Okay, so they will happen at the same time. Okay, they can happen at the same time. uh, so this is what the concurrency actually means and threads actually is. Okay, so I think that doubt is clear to you. Okay, so let me just move back towards that what we wanted to see. Okay, so there is now another term that you have to keep in your mind. Now we are starting the lecture. We just look at the what the basics required for these all lectures, for this whole lecture. So the term I have to start with is critical section. Okay, so before starting with this critical section, I'll just tell you that with an example. Okay, let's suppose there is a counter. There is a count variable. Okay, there is a count variable which is initially 0. Okay, so you can just think, you can just mark it as that it is a resource. Okay, it is a resource which will be okay, so this is what the resource. Okay, yeah, RRSC, you can just think that it is a resource. Okay, okay, resource. So what is happening, that P1 and P2 are working on this count simultaneously. Okay, are working uh, on this simultaneously. So what happens? P1 enters, and what it does to count? It says count plus plus cnt plus plus. Okay, then p1 goes out. Okay, not goes out, it stays in the, what you say, it is actually acquiring this count, but it does not do anything for some time. So here, what the value of count would be here? 1. Okay, count value would be 1 here. After that, what p2 do? P2 also comes in. P2 also comes in, and do count plus plus. Count plus plus. Okay, now here, what's the value of count value would be 2. Okay, and there is another process that another part that has to be performed by P1, is that it has to print the count. Okay, so it will say cout count. What will happen? The value of count which P1 wanted was 1. Okay, but because P2 was also acquiring it at the same time, what's the value of count will become? It will become 2. Okay, so this count was our critical section. Critical section refers to those all resources which are shared among different processes. And the thing that happened here, that P1 did something on a count, and it got a wrong value, is known as the race condition. Okay, that due to the multiple processes working on a same shared memory, there are inconsistent results. Okay, so this is a race condition. Okay, so you will be asked directly that what is race condition in your interviews, and if you provide this example, I think it would be very good. Okay, and just tell me that if you have any doubt in this, that what is critical section, how did the race condition happen. Okay, just tell me that if you have any doubt in this. Okay, so there are method to solve this race condition. Okay, there are method to solve this race condition, so those we will look after, if this particular thing is clear in your mind. Okay, you can just ask anything about related to this if you want. I think no one is having any doubt. Is it, though it is simple, but okay, nice. Mm, so can you simplify the critical? Okay, definition of race condition. Okay, so race condition is actually a condition which occurs when a multiple processes works on a same shared memory or shared resources. So it leads to the inconsistency of data, which happened with the P1, that it did count plus plus, and it wanted that the answer that it will print would be 1. But what happened? P2 comes in, it do count plus plus, and an inconsistent data is printed by P1. Okay, okay. So the shared resources is also known as the critical section. I think I am clear in this part. Oh, okay, okay, nice, nice. Okay. So I think you all doubts are clear. You have no doubts because it's also basic. Okay. So in from today's lecture, very easy questions are asked in the interview that we will see in the end also, right? You will be directed. See, I provided these notes to the DevTown team. Okay. So I have not prepared the link for now. Okay, so they'll definitely share those notes with you. Okay, so don't worry. See, day one I shared by myself because I thought that many of were didn't you got that notes, but I think I have already shared with the DevTown team. They'll definitely share. Okay, so don't worry about it. Okay, and if not possible, what I'll do one thing that I'll come tomorrow, and would share day one, day two, day three, day four notes with you. But actually, what happens that okay, notes are shared already, right? So someone told, right? So you be active in the community group, okay? Because what happens, you all are not available at the same time in the class, right? Okay, so someone told that when two processes or more processes want to occupy the shared resources, then the race condition happens. Kind of, you are partially right, but race condition is when the data becomes inconsistent. This is the first step, and after that, if the inconsistent data is produced, right, then it is called as the race condition. This is the first part, and after this, what should happen? That processes should have inconsistent data. Like P1 wanted the count to be one, count value to be one, but what it printed was two because of P2. Okay, and simultaneously, what can happen? That after this printing, count is decreased by one. Let me just do what happens here. And what P1 do? P1 do count minus minus, and and P2 says after that that I want to print this count. Okay, print this cout count. So what will happen? That what will be printed here is one. Okay, so how it lead to inconsistent data? That P2 wanted to be two, but because P1 entered at it decremented this count, so because of that, an inconsistent data is produced. Okay, so we'll use some of like locking techniques, kind of locking techniques, that when the P1 will execute its all operation, like decrementing, incrementing, then only then this particular critical section would be free. Okay, so our whole motive would be to lock the critical section when something is there in it, and to free when that particular operation is done, so that for that particular operation there would be a consistent data. Okay, race condition, when multiple threads access the same data simultaneously causes, right, right. Okay, you are very correct definition. Okay, any doubt? Because if you have any doubt in this particular case, then you'll not be able to understand these mutex and all those what you say, flags, mutex, and semaphores. Okay, okay. So if you have any doubt, you can just ask me. Okay, okay. So if you are not clear with all those things, then you'll be having very what you say, difficulty in this particular case. Okay. Okay, so I think what someone is asking, real life of example of critical section. Okay, so have you have you gone to ticket booking site? Have you ever gone to? But what happens? Okay, what happens in that? If no flags and semaphores are not used in it, that there is a last ticket of the bus. Okay, and there is two users which have login into this particular what you say, to this ticket booking site. Okay, what will happen? This particular ticket would be shown to both of the users as true, like this particular seat is empty. Okay, so what happens that both of them clicks on this particular seat and pays for it, so it leads to the double pay. Okay, but now what have systems has provided, this thing would happen, but what by using flags and semaphores and mutex, what we'll do, we'll return the payment of one user. Okay, so this is the real life example of semaphore, or what you say, critical race condition. Okay, so some of you must be thinking that it would be good that we use flag. Okay, I think not flag. Flag can be anything. You can just say is empty. Okay, you can make a bool expression. That bool expression would tell. Bool expression would tell. Okay, the text color has been changed to this. Okay, okay. So flag is nothing. Flag is a bool expression. Bool. Bool, I think all of you know that what is bool expression, that it can have a two value, that is it is either true or it is either false. So some of mind you think that flags would be good, but flags are not a good idea at all, and I'll tell you how. So okay, so if you are using flags, then this condition will occur that I just told you, that what P1 and P2 will see for the first time. If flag is false, flag false means that there is no process. Okay, there is no the what you say, the flag false means that there is no process in the critical section. Flag flag f means no process in critical section. So what it will do, when p1 and p2 comes, when p1 and p2 comes, p1 and p2 comes, so I am giving just example of with two processes, but there can be many. What they will see, they will see that flag is false, and what they too will do, they enter the critical section at the same time. Okay, but then what would be the advantage of this using flag? There would be no advantage, and it would lead to the same, what you say, the race condition. Okay, so flag is not an option at all. Okay, not an option at all. Okay, okay. So this is all about the flags, and I think whenever interview will ask that why, what you say, why flags are not an useful thing, then you can answer in the similar manner that p1 p2 comes, they will see that flag is f means no process in the critical section, and what will happen, they both will enter at the same time. Okay, so we need a kind of a strong mechanism that even if two processes see that the critical section is empty, we want that only one should enter. Okay, so we want that one should enter, and we'll use mutex in it. Okay, let me see, someone asked something. Okay, someone asked her notes have only typed pdf. Okay, I'll share those. Okay, no problem, I'll share those. ठीक है, right? So is this thing clear that why flags are very kind of a, like, it might seem for the first time that yes, these can be used, but I told you the loophole that is present in this system. Okay, if p1 p2 come simultaneously, if they are coming like one after another, then it's not a problem. But I think there can be edge cases that you have to think of while programming. So if both comes, they'll see that flag is false and they both will enter, and this similar kind of situation will happen that we just saw, that what happens when p1 and p2 enters the critical section at the same time, it leads to the race condition. Okay, so tell me that if you have any doubt related to this particular thing. Okay, so if you have no doubt, you can just say no also, so that I can just move forward. Okay, nice. No, sir, no doubt. Okay. Ma'am, very nice session, ma'am. Okay, nice. Okay. So what's our need? Instead of using flag, what is our need? Our need is that we want something more strong. Okay, we want something more strong, and our second, what you say, second need is that it should not only work for P1 like two processes. We want it for work for three or four or 10 processes. Okay, okay, so we'll satisfy our first condition first, that we want a strong mechanism so that it can cater the need of P1 and P2 processes, like two processes. Okay, okay, so we introduce the mutex. Okay, so I think this would be a very good picture. This is a what you say, this is the very good example that I got. I thought that it would be very great for you to show that. I just told that we want a very strong mechanism. Okay, we want a strong mechanism, right? So what this mutex provides us, it provides us lock. Lock means when P1 will enter, when P1 will enter the critical section, it will lock that particular, what you say, it will lock that particular critical section for the thread A only. Okay, so what happens that when P1 thread, suppose thread A, thread B are there, when thread A comes in, it says lock M, means lock this particular critical section area, that any other thread would not even going to look at this particular section. Okay, and you will see that how the data consistency problem is actually solved through this. Okay, let me just make it some. Okay, so suppose we look at the what you say, we looked at the example of counter. So this particular operations, so what we did, we said counter is equals to counter plus one, and what we do here, we'll print it simultaneously. Okay, we'll print it here simultaneously, and what will happen, what you say, see out count. Okay, counter. Okay, so what happens, thread A actually increases the one thing in it. So initial value of counter was 0, and what will thread A will achieve, thread will A achieve the value that it wanted, that is 1. Okay, after that what it does, it unlocks M, means it's free that particular resource. Then what happens after that, lock B will enter, it will lock that particular M, increase the counter value, this counter value will become 2 here. Okay, this counter value will become 2 here, and after that we'll just print the same statement. Okay, let me just bring this statement here. Okay, and what will be the output, output will be 2, and this is what the thread B wants. Okay, and no race condition is actually achieved in this. Okay, no race condition is actually achieved in this, and this was happening before using any kind of, what you say, mutex or locks, and this is what we achieved after what you say, after using mutex. So mutex means mutual exclusion, है ना, right? Its full form is mutual exclusion. So mutual exclusion means that you are isolating one thread from the outer environment. Means when this thread A enters, it have a proper full right to do everything that it wants to do with this particular, what you say, critical section. Okay, and that we saw also. It will lock it. So until and unless it is unlocked, and no other thread would look into it. Okay, look into it, right? So I think mutex would be clear. So what was our first demand? We want a strong mechanism of locking. So this is achieved using mutex. Okay, so this particular thing is achieved mutex. What's our second need? Our second need is that it should work for 10 or 15 processes, not just for two processes. So what we introduced semaphores. Okay, so we'll look at the semaphores afterwards. But first tell me that is this mutex thing is clear to you? Okay, so tell me that is this particular what you say mutex thing clear to you? One minute. So we need the same nodes to through TG. Okay, why race condition is not achieved? Because we got the output that we wanted by locking the critical section once. So we achieved what we wanted. Okay. 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 Yes, I think all things are clear. So I'll answer that why race condition is not achieved. Okay, so yeah, thread is nothing. They are just sub part of a process, and that's why they are called the lightweight processes. And we divide them in a such a way that they are independent of each other. So as they would be independent of each other, it would be easy for us. Okay, it would be easy for us to work with them. Okay, this is what the threads can be perfectly defined. Okay, okay. So what's our second need? Okay, our second need is that we want this particular thing to work for 10 or fifteen processes. Okay, so before you, okay, so here it is written wait. Okay, here it is written wait. I think there must be some issue. So here it is written wait. Okay, here it is written wait. Let's change color to oh. So here it is written that it is wait semaphore. Okay, or I can just write this is referring to the wait. Okay, so this is actually more logical part. So keep your logical mind open for now. Okay, once you understand that what is this wait and signal are, it would be easy for you, and you'll understand that how the P2 P4 like how it can cater the need of 10 like two or more, like more than two processes. Okay, I have also bring some of the examples. So okay, so what this wait will do, wait wait will do s minus minus. So what happens if there are two resources, if there are two resources and three processes. Please be very attentive what I'm saying, that there are two resources and three processes. There are three P's. Okay, I'll refer them as P's, and there are two resources. Okay, okay. So you will call wait on suppose and what we want, that P1 will come first, P1 will come first, after that 2 will come, after that 2 will come, and after that 3 would come. Okay, this is the scheduling that we want, that this is how the scheduling would happen. So what will happen, we will call wait on p11, and what will happen, as there are two resources only. Now as we called on the wait, okay, as we called on the wait, it will become s minus minus. Okay, s is equals to s minus 1. Now resources will become 1. After that p2 will enter, p2 will enter, and the s will become 2 here. S will become 0 here. Okay, s minus minus. Okay, and when process 3 will enter, it will call on the wait condition, as it wants the resource. You can just think that wait would be called by the process when it wants the resource from the critical section. So what will happen, it will stuck in this loop. Okay, it will not go to this particular line because as resources are 0. So what will happen if resource if s becomes 0, it will get stuck in this loop and will not go out. Okay, means no resource would be allocated because we had two resources only and three processes. This resource would be available only when the signal is provided. Okay, so suppose p1 gets out. Okay, p1 gets out and it will signal the semaphore. So now from 0, from now 0 it will become 1. 1, and what will happen after that, p3 will get out from this particular trap position, and it will do s minus minus, means it will acquire the resources. And again what will happen, from 1, from 1 our semaphore will become 0. Okay, so semaphore is nothing. It is actually an integer value, which actually tells about the what's the current state of, what you say, state of critical sections. Okay, so this thing would be more clear here. That suppose there are p1 p2. Suppose let's just do for two processes first. Then we'll go for three processes. Okay, it will be clear. It will be clear. Wait for a minute. Wait for a minute. It would be clear. So first of all, tell me, are you clear about that? What is wait and signal are doing? They are doing nothing. Whenever a process will come, it will call wait. Okay, so wait will do one thing. Wait will do two things. Either it will s minus minus, or it will see that if s is already 0 for now, means there is no resources. It will trap that particular process in something else. It will say, okay, I'll share with you the resources, but till now I have no resources left with me. Okay, so this is what the wait will be doing, and what signal would be doing. We'll be referring this signal once we leave the resource. Once the process leave the resource, it will signal that I have left the resource. Means your one resource is empty, and we'll add that particular one to the total resource that we have till now. So this is what about wait and signals are. Okay, wait and signal are, and we'll so just tell me that if you have any doubt in this wait and signal. Wait and signal are clear to you? Okay, just tell me that first, that if you are clear about wait and signal. Okay, I think no one is having any doubt. It's great. So now we can move. We will see that there are two processes. Just look this particular thing very carefully. Okay, then it will be all clear for you. So what we are having, okay, nice. If you're clear with what wait and signal, that you have p1 and p2 as two processes. Okay, there is only one resource. One resource means there is only in critical section there is one resource, which is one printer. Okay, as there is one resource, what would be the value of semaphore? Okay, I think I have shown, but okay, it's very much logical that semaphore value would be 1. Okay, because we have one resource. Okay, keep this thing in mind. Semaphore, this value of s is representing the total amount of resources that we have for in the current value. Okay. So the code idea is that wait and signal. I think this is a this these two terms are clear to you, that what is wait and signal. So what happens? Okay. 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 So what happens when P1 calls wait? Means P1 enters the critical section. It calls wait. So what wait will do? Wait will subtract that s minus minus that I just show you. That it will do s is equals to s minus 1. Okay. So now what would be the value of s? S will become 0. When P2 calls on s is already 0, and I told you that when s is 0, this wait call will keep this p2 in a trap, or you say in a block condition. Okay, in a block condition. Okay, as it sees as p2 calls on s, it will see that s value is 0. So what the wait condition will do, it will keep in a trap. It will keep it in a trap. okay, or trap, or you say in a what you say, in a blocked condition. Okay, so what happens, p2 is in blocked condition now, because s value is 0. S value is 0 means there is no resources for you now, so please wait. Okay, then p1 finishes. As p1 will finish, what it will say, it will signal out, okay, you can just increase your value to +1. Okay, so it will do s is equals to s2 to 1. Okay, from 0 it will become 1. So after that p2 will awake, and p2 will call on wait. Okay, p2 will call on wait, and what happens when p2 will call on wait, from 1 it will become 0, and the similar pattern would be followed as followed for the p1. And in this manner they will independently execute their processes without interfering in each other's part. Okay, I think this particular thing would be clear, and we'll look at the example of with the three processes. And now I will ask some of the questions with you. Okay, before starting with this. Okay, so if we have three processes, and I am having two printers, means I am having two resources, then what would be the value of s? Tell me that. If there are three processes and I am saying that there are two printers or two resources, then what would be the value of s? Okay, tell me the what would be the value of s? Okay, nice, someone said 2. Okay, no, why 1? There would be no 1. 2, there would be 2, because there are two resources, then the value of s would be 2. Okay, okay, many of answers are coming 2, 2, 2. Okay, nice. So I think this thing is clear in your mind. Okay, tell me that. Okay, now wait. 2. Okay, okay, we got what is 2. Now tell me that when I will call on wait for any one process, what would be the value of s then? After calling one wait, one time a wait, what would be the value of s? What would be the value of s? Wait a minute. Right. After calling one wait, what would be the value of s? Okay, it will be 1. If I'll not free, if I not call signal now and call wait again, then what would be the value of s? I have not called on signal. Just tell me that what I have called again wait, then what would be the value of s now, or the total number of resources that you have? Okay, right. It would be 0. Right. Answer is 0. If you call two simultaneously wait, means you have acquired two resources. You have not called on signal. I think this point is clear. I think it would be easy for you to now understand that what is happening with the three process. Okay. So what is happening? You have three processes, P1, P2, and P3 with two printers. Okay. And as you have two printers, you all answered very correct that S would be 2. S would be 2. What this weight would be doing, it would be doing S minus 1. I have already told you, if S becomes less than 0, or it becomes is equals to 0, it keeps in a trapped position. It keeps in a trapped position, or you can say it will block it. Okay. So before entering the what you say, you can also say that before entering the critical section, every process will call on wait. Okay, because then only it will get to know that resources are available or not. Okay, and when the process will be leaving out, means it will be executing its whole processes, it will call on signal. It has to call on signal because it is leaving the resource, and it will and we know, and it has to make sure that others should also know that I have left the process. Okay, so keep your mind here that what happens, that P1 will come in, it will call on wait. Okay, I already asked you that what will be value. You answered all correct, that it would become 1. Without calling on signal, I'll call P2. P2 calls wait. Then what will happen, from 1 it will become 0. Okay. After that, when P3 will try to call on S, it will see that it is value of its value is 0, means there is no printer left. Okay, no printer or no resources left here, so it will be in a trapped position, or you can say in a blocked condition. Okay. Okay. So okay, so this is about this. So now I'll again ask you some of the questions. Now when p1 will leave, p1 will leave the p1 will execute what, on what out of wait and signal it will call. It will call on wait or on signal, and after calling on signal, what would be the value of signal? Answer these two questions. I think attendance link has also been dropped, so I think many of student have gone. Okay, so okay, just tell me these two things, that when when now when p1 calls on what p1 will call, it will call on wait or signal after execution, after its execution. Just tell me that. After completing, what it will do, it will call on wait or on signal. So yes, someone said that it will call on signal, right? It will call on signal. And just tell me again, that after signal, after calling signal, what would be the current value of s? What would be the current value of s? It was 0 before. After calling on signal, what would be the current value of s? Okay, 1. You're very correct that it would be 1. So when P1 finishes its job, it will call on signal, means from 0 it will become 1. P3 will awake, and P3 will call on wait because it will be acquiring the resource. From 1 it will become 0, and P3 it starts functioning, and simultaneously you will release for P2 and P3. And I think this particular part is very much clear to you all, because you all answered in a very good manner. Okay, like not uh, like all there was the majority of correct answers. Okay, so I think we can just look at the interview questions that are asked. Okay, so these are day 3 notes. So we covered the what is critical section. Okay, you can just see that race condition. Okay, what okay, the so race condition would be clear. Locks and mutex would be clear. That what is mutex? Mutex refers to the mutual exclusion. Okay, semaphore is clear. Okay, what are semaphore? Okay, you can just think of this mutex versus semaphore. Mutex is used for two processes. Semaphore is can be used for multiple processes. Okay. Okay. Okay, I'll share these flow charts. Okay, they are in here. I think some here. I'll definitely share them. Don't worry. Don't worry. Okay, so I think we can. Uh, okay. I think we can start with the interview questions. That what are generally asked. Okay, and there is one homework for you all. That just go after this lecture and read about these 3 case studies. Read about these 3 case studies. That what are these? First is a reader writer problem. Reader writer problem. Okay, reader writer problem. Uh, okay. Wait a minute. Second is producer consumer problem. Producer consumer problem. Okay, and third is, though I have mentioned them in the what you say, in the notes. Okay, like the amount of content of these 3 are that much that are asked in interview. Okay, and dining philosopher problem. Dining Okay. So before just I'll give you the brief intro of all these three. These three are actually based on what you call race condition, and you will see that the solution of these all three are provided using semaphore, semaphore plus mutex. Okay, means not like always these two would be together, but you will see that these problem solution would be provided by this. Okay, so someone literally asked about that what is the real world example. So I told that the sitting book arrangement, right? If there is one seat, two users would see that there is this particular seat would be empty. Okay, so producer consumer is like similar, right? Right, because producer should not produce more than the amount that is required. Consumer should not consume when there is nothing in the what you say buffer section. So like these problem, like, right? So the critical section types of problems these are, and these are solved using semaphores and mutex. Okay. Okay, right. So just read about them. They are not as much, but definitely this would be asked that how can you solve them, and you'll simply answer that they can be solved using semaphore and mutex. Okay, so this is all about those. So let me see that if there is any question that is tricky, and then I'll ask you because what is critical section? Everyone can answer that the part of code which can be shared, accessed. Okay, we saw that what is critical section. What happens if two threads enter the critical section together? Okay, so answer me that what happens that when two what do you say two two processes enter the critical section. Okay, so answer is very much clear. Race condition will happen. Okay, okay, right. Race condition would happen. Someone with sh- this particular person give a right answer. Then okay. Mutual exclusion is very much clear. Mutual exclusion is one at a time. Okay, and that's why we moved to the semaphores, because semaphore provided us with the solution of what you say like n numbers of processes synchronization. Okay, these would be clear to you. Okay, these are very simple. Okay, so what are semaphores? You can say that they are synchronization tool, and you can call on wait and signal, and you can tell that what the wait condition do and what is signal do. Okay, so wait, what the wait do? The wait is actually tells the process that is there enough resources available. If it will be available, it will subtract that resource. But yes, if there are zero resources for now, it will lead into a trapped condition. Okay, it will leave into a trap condition. I think all things are clear. These are things clear. See, there are two types of semaphores. So binary semaphore and counting semaphore. So if there are two processes, that semaphore condition would work as a binary semaphore. But if there are n number of what you say processes, it would work as a counting semaphore. So I think this is very much clear to you. Okay, so did you got my point that when there will be two values as the semaphores are built so that they can work on any kind of processes. So they are also what you say, they that particular semaphores can be used for the two processes. If they are used for the two processes, then they are called semaphores, binary semaphore, right? And if they are working on two processes, they would definitely work similar to the mutex. Okay, but they will definitely work similar to the mutex. But what is difference between mutex and binary semaphore? That mutex is using lock and unlock condition, and here we are using wait and signal condition. Okay, so this is all about these things. If any doubt, you can just ask me. Otherwise, if you have no doubt, do fill out the attendance form and you can leave the class. Okay, if you have no doubt, you can leave the class. I'm looking at the chat session. Sir, please tell the critical section again, not the race condition. Okay, Okay. Okay. Hmm. So this is a count. Okay, count is a resource which is shared by the P1 and P2. Okay, so the area in which this count is being provided to these processes is called as critical section. Critical section is basically nothing. It is a share. Let me just okay. So critical section is nothing, but it is a what you say shared. It is a collection of shared code resources which are provided to like n numbers of which can be provided to n number of processes. So critical section is nothing. It will have all the resource. Let me just write resource. It will have all the resources that can be okay, resource that can be shared between all of the processes, and this all resources code, okay, code is known as like the collection of these all resources and code will known as cs, that is critical section. Okay, so if your doubt is clear, then tell me that okay, it's clear, because how will I know that I cleared it out? Okay. Okay, nice. Any other? Just tell me and do fill out the attendance form. Okay. See, you can talk. I think 1 day grace is given to all. Like, not all. If someone missed that, 1 day grace is given. Okay. Someone tell. So, someone just told that note links would be provided by the DevTown team only. Okay. So notes would be provided by the DevTown team only. Though I have shared with them. Yes, I have shared the day three notes. Okay, so that's perfectly fine. Any other doubt? You can just ask me. Okay, because we'll bind up the session then. Okay, within 2-3 minutes, and do fill out the attendance form, right? All of you who are present here. Otherwise, it's over for tonight. Goodbye. Like if you have no doubt. Okay. I think no one is having any doubt. Every doubt is clear. Okay, notes would be provided. Don't take much tension about notes. Okay. Goodbye, everyone. If your doubts are clear, good night. Good night. So please share. Definitely tomorrow I'll share all these flow charts. Like you want what you want. Like the these things. Like what I just told you here, that these all. If you are asking these all, what you can do that you can just take the screenshot of these all. Okay, because what we like before starting, I just told you that I'll just tell you simply that what this particular term would mean, and you will then you will look at the notes and will revise accordingly. Okay, so you can just revisit all these what you say lectures. Okay, I think uh, we cleared almost everyone doubts related to even notes also. Okay. Okay. No, they are provided on, I think, what you say, on WhatsApp community group. They are provided on community group. See, you can ask about these 2 days attendance to the what you say, any like I think they have provided for this that if you have missed any 2 day attendance, because yesterday someone just answered this that if you have lost your 2 day attendance, like if I have missed, then you can contact the DevTown team and ask for the like. Okay, so I think all doubts are clear. We can end the session. Okay, goodbye, everyone. Goodbye.